Good morning. We are Group Church. Today we will give you a presentation about context switching. In today's digital world, multitasking is key. We juggle emails, social media, work documents, and more all at the same time. But what's really happening behind the scenes? This presentation will explore the concept of context switching, the hidden costs of multitasking, and how to optimize your workflow for better productivity. Now first, what is context switching? Imagine your computer CPU as a juggler. Context switching is like the juggler constantly throwing one ball into the air to catch another. The CPU can only truly focus on one task at a time, but by rapidly switching between tasks, it creates the illusion of multitasking. So this is the concept of context switching. Now, why is context switching important but necessary for us? Context switching is the heart and soul of multitasking. Without it, we cannot do running one program at a time, significantly hindering our productivity. It also optimizes CPU's usage. While one process might be waiting for data from a hard drive, the CPU can switch to another process that is ready to run, preventing wasted cycles. Ultimately, context switching provides a smooth and efficient user experience by creating the impression that multiple programs are running simultaneously. Now, types of context switching. There are two types of context switching. First, process context switching. Second, thread context switching. A process context switch involves switching between different processes, while a thread context switch involves switching between different threads within the same process. Both types are essential for multitasking capabilities of an operating system. Now, components of context switching. To understand context switching, we first need to know that constitutes the context of a process. The context includes CPU register, the program counter, and memory management information like page tables. All this information is stored in a data structure called the process control block or PCB. The CPU registers and the program counter are crucial as they store the current execution state of a process. Now, steps of context switching. Now let's walk through the steps involved in context switching. First, the operating system sets the context of the currently running process to its PCB. Next, it updates the PCB with the current state and status of the process. Then the scheduler selects a new process to run. Now, the context of the new process is loaded from its PCB to the CPU register, and finally the CPU resumes execution of the new process from where it left off. Now, some examples of context switching. Let's look how different operating systems can handle context switching. First is Linux. Linux uses the completely fair scheduler which aims to provide fair CPU time to processes. Next is Windows. Windows employs a preemptive multitasking scheduler allowing the system to interrupt a running process to schedule another one. And another was macOS use a hybrid scheduler combining features from various algorithms. This real-world implementation demonstrates the importance of efficient context switching. In conclusion, we learned that context switching is a vital component of operating systems enabling the multitasking capabilities that we rely on daily. While it introduces some overhead optimization technique and efficient scheduling algorithms help manage this. Understanding context switching gives us a deeper appreciation of the complex processes that keep our computers running smoothly. So this is my presentation. The next page is the reference and thank you for listening. Good morning. We are Group Church. Today we will give you a presentation about a famous scientist, Alonzo Church. Alonzo Church was an American mathematician, logician, and philosopher
whose work profoundly impacted the development of theoretical computer science. In this presentation, we will explore the Church's significant contribution to the field, including his groundbreaking theorems, the invention of lambda calculus, and the formulation of the Church Turing thesis. Now, his early life and education. Alonzo Church was born in Washington, D.C. in 1903. He demonstrated a strong aptitude for mathematics and logic from a young age. Church pursued his academic interest at Princeton University, where he received both his bachelor's and doctoral degree in mathematics. His doctoral dissertation completed in 1927. Next, he focused on alternatives to Zembalo's axiom, a foundational principle of set theory. Now, some of his major contribution in mathematics. First is Church theorem. A major contribution of Alonzo Church is Church theorem, which proved the unsolvability of the decision problem. This theorem demonstrated that there is no general algorithmic method to solve all mathematical problems. Now, one of the Church's most significant contribution is the development of lambda calculus, a formal system in mathematical logic. Lambda calculus provided a foundational for functional programming languages and influenced the development of modern computer science. Now, another major contribution is Church collaboration with Alan Turing led to the formulation of the Church Turing thesis. This thesis proposed that any function that can be computed by an algorithm can be computed by a Turing machine. This concept is fundamental to our understanding of what can be computed and forms the basics of theoretical computer science. Now, Alonzo Church authored several important publications, including An Unsolvable Problem of Elementary Number Theory in 1936, The Calculi of Lambda Conversion in 1941. He also contributed extensively to the Journal of Symbolic Logic, helping to the shape of the field of mathematical logic through his research and writings. Also, Alonso Church's influence extended far beyond his own lifetime. His work laid the groundwork for the development of computer science as a discipline. Concepts like lambda calculus and the charge Turing thesis are integral to our understanding of computation. In conclusion and legacy, we can say Alonso Church's contribution to mathematics and computer science have had a great lasting impact. His pioneering work on lambda calculus and charge Turing thesis revolutionized our understanding of computation and logic. Church's legacy continues to influence and inspire achievements in these fields today.